That's better. Yeah.
Okay.
Is that coming through okay?
Yes, everything is okay, Dr. Rob.
Okay.
Okay, hi everyone. Welcome to the meeting seminar today. So today, it is our great honor to meet Dr. Rob from Dyson Robotics, a famous company at the United Kingdom. He graduated Bachelor at Cardiff University, Master of Engineering, and PhD degree in Information and Decentralized Systems at the Brighton University. Rob is a senior principal engineer and is the technical lead for the 360 Heurist robot, a big-market commercial robotics vacuum cleaner and the most complex product at the market from Dyson today. He is a UK Royal Academy of Engineering, a visiting professor at Imperial College London. He has supported teaching at over 20 universities across the UK and the world. He also a chair advisory board for publicly supported projects with more than 15 million pounds. Rob is a chartered engineer, technology fellow, teaching fellow, and learn fellow. So today, Dr. Rob will talk about his work on the robotic vacuum cleaner and focus on a complex autonomous robot, namely 360 Heurist as an example. If you have any question during the talk, please feel free to post it in the chat box, or you can directly communicate with Dr. Rob. And Dr. Rob will answer on at the end of the talk. So, without further ado, let's welcome Dr. Rob.
Thank you very much, Tuan, for that great introduction, and thank you very much for allowing me to present today. It's a great honour for me to come and present at your university, which is fantastic. The title of the presentation today is 360 Heurist, a complex autonomous robotic system. And what I'm trying to do in the presentation is to highlight that the work that you're learning on your engineering degrees is really useful and important for technologies that can be applied across the world. And this is just one example. Okay. So I know a bit about you, that you're students at the university. You don't know that much about me, so I thought I'd give you a brief introduction in a couple of slides just on my kind of career and why I'm here today. As we've mentioned, my day job is at Dyson, and it's a fantastic job because it's really broad. On some days I'm working on a whiteboard and coming up with concepts for new robotics. I also get to work on the full breadth of making robotics, from helping the design teams to decide which work tasks they are carrying out to reduce risk and get a high quality product, all the way to supporting the robotics teams when they need to do over-the-air updates of software, which we do to make the product better even after we've sold it. I also have a teaching role, as we mentioned, at Imperial College in London, which is again a fantastic opportunity for me to share my experience with students. And I received some funding from the Royal Academy of Engineering to support my teaching. And although this was focused at Imperial College initially, I've now taught at universities throughout the UK. And there's some examples there, and also throughout the world now with some more examples there. So that's a little bit about my teaching. I've never been a full-time academic. My working life has been as an industrial engineer, and I've had the opportunity to work on a number of projects. I've worked on satellites when I was a young engineer, not much older than you, and this was a fantastic opportunity to work on products that would go into space. So it's quite nice to think of some of your work that's gone into space. I was working on the Orion 1 satellite system, which was a communication system. So again, it's great to think that your products are helping people communicate. I also went to spent time at Sydney University looking at unmanned air vehicles. And this technology now is being used in Australia to look at crops within farms so that they can decide where, some parts of the farm need more water, some need more feed, and some are ready for cultivating. So again, it's really nice to think of products that you've been working on helping to feed communities. And finally, in the year 2000, I went to a startup company. I was going to be a millionaire and be able to retire. That didn't quite happen, but it was a great opportunity to work on system-on-chip devices. And one of the parts I worked on sold 12 million parts, and this chip would work in set-top boxes, which are entertainment boxes which sit underneath your TV and provide video and audio to your home. So again, it's really good to think of products that have sold in large numbers that you've been involved with. As I mentioned, as an engineer, I've had opportunity to work around the world, from in different parts of Europe and around other parts of the globe as well. And I've had lots of opportunities to study and also to liaise with institutions, and I'd encourage this for the engineers, for the young engineers, because you get a great network of and a good resource of experience from those institutions. I'm always quite sad when I present this slide, because my career is coming to an end and the students' careers are just starting. So you've got all this fantastic technologies and projects to work on in the future, and I've only got a few more before I retire. So I'm a bit jealous. So that's just a little bit about me and my background. I'll now talk about get into the kind of the main part of the lecture, which is to do with the 360 Heurist. I'll start by looking at the main subsystems, and then we'll delve into some of the robotic technologies. I'll finish off by showing some of the future work that we're looking at to do with simulation technologies and the application of AI to some of our products. Okay, so when you're making a robot, it's really important to think about the payload that the robot is carrying. You don't generally make a robot and then sell it just as a robot. It has to do some function for you, and those functions can be, from cleaning your carpet, like the one I'm going to describe, or it could be cutting your grass or working in a factory. So on the 360 Heurist, this is the payload we have, which is a cleaning system, and this all starts with the I think, I'm not sure you can see my mouse there. It all starts with the brush bar, and this has got a 25 watt motor which is rotating the brush bar, and it has the brush bar has bristles on it which beat the floor to agitate the dust, so that gets the dust into the air. The other important part of the system is the vacuum motor, and on the Dyson, on this product, the vacuum motor can go up to 100 watts, and then this provides an airflow through the system from the floor through the bin, which is also a separation system, and then through and out of the back of the robot. So now the brush bar has agitated the dirt, it's in the air, and then we pull it through the separation bin. The separation bin has the air spinning around, which means that centrifugal force will push the dirt to the side, and it'll hit the side of the bin, and it will drop down into the bottom of the bin. Inside this section here, we have 8 cones. So which is called the root cyclone system in Dyson terminology, and the air that goes into this bit spins even quicker because of the size of the cone, which means that we can then push the really small bits of dirt in, and they hit the side and they fall into the middle of the bin. The air continues its journey, and eventually it is pushed out to the back of the motor. We have a filter at the back just to make sure that we don't push dirty air back into the atmosphere. So that's just a quick overview of the cleaning system. But we do have to. This has impact on other aspects of the product. For example, because we're moving air across the surface of plastics, we get a buildup of static electricity that we need to be able to cope with. So again, the payload can have an impact on the robotic elements as well. Another important aspect of the robot is that the user has to be able to interact with it. So we have 3 aspects to the user interface. The first is that the UI on the actual robot. We have an app, which is fantastic because it allows you to have better control and have more information from the robot. And we also integrate it with the home network, for example, with Alexa, so that you can control it with voice. The UI on the product is fairly simple. It's got one button, so you can just start it, pause it, and stop it. And then it has a number of indicators to show the status of the robot. So and these include the level of battery, the amount of energy that the battery has left. It also indicates the Wi-Fi and if you're connected or not connected. And then it has a couple of fault indicators, and these are to do with either the airflow, the traction, or the brush bar, if there's any faults in those. So for example, if a piece of clothing has gone into the cleaning system, then we can detect that and inform the user. The app is fantastic, as I've mentioned, because it gives you lots more information. With the robot, for example, with the robot, when it drives around, it builds a map of the floor area in your house, and then it will send this to the app, and then with your finger you can then cut the map that's provided into sections, and then you can label the sections. So you can say, number 2 would be my hallway, number 3 would be my kitchen, number 4 would be my dining room, and number 1 would be another room. And then what you can do is you can associate with the rooms characteristics. So you can say, I want to clean my hallway at a high power, and I want to clean my kitchen in a low power. And you can also associate scheduling, which means that you can tell it what time of the week and day to do the clean, and then the robot will go out and do that during the day. You also get a lot of information back from the app, so it will tell you what coverage area you've had, which rooms it's been into, etc., which is again really useful. And finally, with connecting to your home network, this can be really useful. If the cleaner is running while you're at home, you can then command it via voice to stop if, for example, you have a telephone call to take, or if somebody comes to the door. So again, that's quite a useful feature for the product. Another important part of the system is the power system, and here at the center of this slide is the battery. Okay, and the battery has about 78 watt hours of energy, and this will allow the robot to do in the kind of medium power, it will allow a clean of about 40 minutes. When the robot has run out of energy, it will come back to the dock. You can see the dock represented over here. The dock has 2 charge points, which are at the bottom of the dock, as you can see here, and they connect to 2 charge points underneath the robot. In fact, to stop to make sure there's no accidental shorting of these power pins, there is an RFID tag within the dock, and then on the robot there's a small antenna. So when the antenna is above the RFID tag, then the dock knows that the robot is there and then can apply the power to the charging contacts. We also have these targets on the dock. These are sometimes referred to as fiducials. And then this allows, there is a camera on the robot, which is an upward looking camera, and these fiducials allow the robot to get fine tuning of its position before it comes onto the dock. With the charge time for the battery, which is a lithium-ion battery, it's a little bit piecewise linear. So the first part will charge quite quickly, whereas the second part will take a little bit longer. So if the robot is doing a clean in a large area and needs to come back for a recharge, we don't charge it all the way to 100%. We only charge it to about 80%. And again, because we have statistics through the Wi-Fi network, we know that 95% of customers are able to cope with just having 80% charge for the second part of their clean. Okay, so that's a little bit about the power system. That completes the section on the main subsystems. I'll now go into some of the robotic technologies, and I'm going to start off with the motion system. The motion system comprises of 2 15-watt motors which drive two traction systems, and for the robot we've gone for a tank track arrangement. And again, the mechanical engineers spent a lot of time on designing this. You know, what size of wheels do we need here? There's a belt system. What material should the belts be made of? You know, how deep should the teeth be? What's the pitch between the teeth? So they spent a lot of time designing this and empirically testing it to make sure that we can get around objects in the home. So the types of objects that we need to get around are rugs that you might have in your home, which might be quite thick, or divides between different rooms. If you've got carpeted and hard floor, then you need to be able to traverse from one to the other. It's also important for the traction system, as I mentioned for the dock earlier, so that when the robot gets back onto the dock, when we take power away from the traction system, that the robot doesn't roll back and then come off the contacts. So again, the mechanical engineers spend a lot of time making sure that the tension was just right to keep us on the dock when we were unpowered. So with this traction system, because we've got a circular robot, we can either go forward in a straight line, we can come backward, or we can rotate on the spot. And rotating on the spot is fantastic for a circular robot, because then you can move the sensors that were at the front and then rotate, and then the sensors are at the back. Okay, which is a useful feature. I'll now go on to consider some of the sensors that we use in the robot. A lot of these come from mobile phone development. So here I've got a representation of a time of flight sensor, and this is the size of a quarter of the small nail on your finger. So they're really small and compact, and they give you an estimate of the distance of the object away from the sensor. They work on an infrared technology, which sends out photons of light and actually times, through using a phase difference approach, times the the amount of time it's taken for that photon to come from the sensor, hit the object, and come back, and then you can calculate the distance of the object away. So fantastic technology, and also relatively inexpensive. I think these sensors are, about $1 each, which is fantastic. This next slide shows how we use these sensors. This is a representation of the robot at the top here. The bin is actually on the front of the robot, and we have 2 sensing pods which sit either side of the bin. And in each pod there is 4 sensors. There's one in each side that look down, and these we call the drop sensors. So these detect if we come to an edge of a stair or if we come to a step, so that we don't fall down the step. So if we detect the drop, then we can take evasive action and move back from that area. We've also got 2 obstacle detection sensors at the front. So these point forward in what I would call a cross-sword arrangement. And then as we move forward, we can detect objects in front of us. We also have 2 wall follow sensors. It's important for the robot to be able to get quite close to the edge of the room, because we tend to get dirt congregating in that area. So with the robot, it can get close to the edge to give us a really nice clean, and we can have a kind of a feedback system from the wall sensors to control that. We also have long range sensors, and these see about 2 meters either side of the robot, and these are the sensors that are used to build the map that I showed you in the app earlier on. Okay, so that's just a little bit on some of the sensors that we've got in the robot. Again, for the students, if you've and the academics, if you've been into the lab and used sensors, you will know that they're always fallible. They don't always work as you expect. So we have a secondary system, which is called the bump system, or contact system, and this is based on having 2 switches, one on either side of the robot. So if we bump into an object, then we can detect it if it's on the left hand side or the right hand side. So this is a great kind of backup system. We also have an overhang sensor. So this is just which we sometimes refer to as the rhino horn. It's a small bit of plastic, but it does provide a useful facility. If you look just on the slide here, you can see a copper-colored dome, and that is our upward-facing camera. And the problem is that if the robot was to go underneath a shelf of about the same height, then that could scrape the top of the camera and damage the lens. So the rhino horn is a great addition, so that it can detect if there's a shelf that could damage the lens of the camera. So that's another good feature for the robot, and quite a simple one. Okay, so we've discussed the sensors. We'll now go on to look at some of the patterns that the robot performs. So it performs, one of its main patterns is an oil drop pattern. So this is an outward square spiral that the robot will follow, and this will ensure that we cover the whole floor area, to give the whole carpet or whole floor a clean. We also use grid-based cleaning. So the robot will do a 5 by 5 meter grid, and will endeavor to clean everything within that grid before it starts a new grid. Okay, so that's just a little bit about the patterns. We also have a traverse algorithm. So occasionally the robot will need to go from one place to another. So it might need to go back to the dock for a clean, or after recharging, it may need to go back to its to finish off the clean. So it'll need to do a point-to-point traverse. And the algorithm we use is loosely based on an algorithm referred to as A star. And what the A star algorithm does, if you want to move from the green square to the red square, it calculates a number of paths through the obstacles, which are represented by blue squares, So it'll come up with lots of different paths, and then it will rate those paths. For example, you might want to try and get for the shortest path, but you may want to avoid going near to obstacles, especially if there's a small gap. So you weight your path based on those two criteria, and then you can select the most appropriate. So here the robot may decide to actually go around the outside and avoid this narrow gap here, even though that is slightly longer than taking the more direct route. So that's a little bit about our kind of traverse algorithms. Another important sensor for the robot is the imaging sensor, because this is the sensor that it uses for its navigation. Here I'm showing also the camera system that we used for the 360i. The 360i was the first robotic vacuum cleaner that Dyson brought to the market. And this had a fairly complex camera system with lots of small parts in it that needed to be assembled, which was difficult to do. And also the optical path was quite tricky, because here the optical path is you have one diffraction from an outer lens, which then focuses the light onto a mirror, which is down here, which reflects the light up, which hits another mirror, which then goes through a lens to get onto the imager down here. And by the time we had the 360 Heurist, or we were developing that, again, technology in fisheye lenses driven by mobile phones had made it possible to simplify the 360 arrangement and just have a fisheye lens to replace all the majority of the mirrors and diffractors in the 360i camera. So now we just have one diffraction. In fact, there is a lens not shown here, which helps focus the image onto the imager, but it's a much simpler optical path compared to the 360i. So this is the image here. This polar coordinate image is the image that we get from the camera, and this is me sitting in my living room in Bristol, and I've just taken a quick image. So now you can see the TV down in this section. You can see my fireplace here, and you can see my knees with the laptop that I'm using. The first process that we do with the image is to unravel it. So we take it from the polar coordinate frame to a rectilinear frame, and this is shown here. And this allows us to pick features from the image, and we use corner features in our system because these are invariant to distance from the camera. The robot has to work in dim light, so this might occur early in the morning or late in the evening. So the system has an illumination system which is based on 8 LEDs, and we can control the light coming out of the LEDs from something that's very, very dim linearly to something that's very, very bright. So this acts as a torch for the robot, allowing us to illuminate the environment. And this is again, it can be used in early morning or late night, or in fact, if you're going under tables and things in your home, then again, this helps our navigation. This slide shows some of the hardware and software architecture for the product, and this is primarily split into 2 PCBs. There's a PCBA which refers to the application PCB, and then there's the real-time PCBA. In the middle of the slide here, I show which processors we have. So for the real-time system, it's based on 3 MSP430 processors. So these are small, kind of 16-bit micros. And we have 3 of them. One is dedicated to looking after the UI, controlling the illumination and the button presses. And we use this because this gives us a really good reaction time to the user interacting with the robot and the UI on the product. The robot has, high power motors and a fairly high energy battery. So So we are concerned about the safety of the product. So we have one MSP 430 that just looks after the safety of the product. So it looks at temperatures and currents within the robot to make sure that we're within the correct values. It also deals with the drop sensors of the robot. And the final MSP 430 is concerned with sensing and actuation. So it takes information from the pods and the wheel odometry and then is able to label these and timestamp them before they're sent up to the application processor. It also takes commands from the application processor to control the actuation. And the actuation for us are the vac motor, the brush bar motor, and the traction system, and also the illumination. On the application PCB, we have a high-performance Intel Cherry Trail chip system on chip, and this has a quad-core Atom X5, which runs at 1.4 gigahertz with a boost frequency of 1.9 gigahertz. There's also a crypto core with this system on chip device, so that we can make sure that when we get over-the-air updates, that we can check the validity of them before we install them, and also during boot we check the image that's on flash to make sure that somebody isn't trying to break into the machine. That the chipset also connects to Wi-Fi and BLE. So the Wi-Fi we provide is 2.4 and 5G Wi-Fi, and we use the BLE for giving us a quick connection journey to the product from your phone. This processor also takes inputs from the camera and the IMU, because these are kind of high data rate sensors. We need a large processor to process them. From a software perspective, we've designed our own very thin real-time operating system to work on the MSP 430s, and then the other bits of code are written in the language C. On the application processor, we run Linux, which is a great, fully featured operating system. And then the algorithms, that do the navigation, planning, and facilities and control are all written in C++ by our software teams. So that's just a quick overview of the hardware and software architecture on the product. I'm now going to go and consider one of the main algorithms on the product, which is SLAM, which is simultaneous localization and map building. These algorithms were developed in the mid 80s. They were making their way onto robotics. Before then, in robotics, you were either doing localization or you were doing mapping. So localization is where you're provided with a map from somewhere, and then your robot moves around, does some sensing, and then determines where the robot is within that map. If you're doing map building, it's the opposite. Somebody tells you where you are, and then you use your sensors to then build up the map. And up until the mid-80s, people were combining these two processes, but it was all a little bit ad hoc. And the breakthrough was to put together a mathematically sound approach to doing both the localization and map building together. Okay, so and this is one of my first experiments on doing SLAM when I was a researcher back in BA Systems back in in around the 2000 era. And here what I've got is, let me just explain the SLAM here. So I've put some posts inside the lab, and these are going to be my features. So these are going to be the thing that I build a map of. And I have a robot here, which is a Pioneer robot, and it has a laser rangefinder, which is this blue box on the top. And then the robot drives around. It has to build a map and then localize itself within the map. This is the output of the SLAM down in this here. So this is a plan view of the room, and if you can see these black crosses, This is the ground truth. This is where I've put these posts within the lab. Okay, and then the robot moves around, and then the output from SLAM is that we get a map, and the map comprises of these blue crosses where we think the feature is, or the pole is, and associated with that is an uncertainty bound, and here we've got a 3 sigma bound, if I remember correctly, for that for the position of that feature or pole. You'll also notice that we've got these red crosses, and that's where the SLAM algorithm estimates that the robot is. And again, this has a 3 sigma uncertainty bound associated with it. You'll notice there's 2 red crosses here. In this experiment that I was doing, I was actually running 2 robots, and they were cooperatively building the map. Okay, so that's some of my early work on SLAM. Around about the same time, or just a little bit later, researchers were also looking into how you could do this with a camera, and this is one of the earlier pieces of work on this. So this is at Oxford University in the early 2000s, and we can see Will, one of the students here. He's got a camera, and he's pointing it at the wall, and you can see that there's some posters and stuff on this wall here. And so what's happening is that we're now picking features, and we're picking out corners from the images that the camera is looking at. So we're picking out these corner features, and they're not corners as you and I would think of corners of doors and things. They're just corners in the image. We then did some, there was then some pre-filtering done on the images. You know, to get a good image, we may need to observe it 3 or 4 times before we start thinking of it as an actual feature. So there's some pre-processing, and then you can see the estimates building up here. I'll just stop it there. You can see that the estimate, the uncertainty is an ellipse pointing towards the camera, because the camera is effectively a bearing only sensor. So it gives you a good bearing, but it doesn't give you good distance. But as we move the camera around, we get bearings from different angles, which then helps reduce the uncertainty, and then the uncertainty shrinks down to something much smaller and circular or spherical in shape. So that was just some of the work we did initially, and then at Dyson, the engineers were thinking, this is great technology, and we can use this in the robot. So what we did was we then pointed the camera up into the air. So our camera system can see between, you can see 360 degrees all the way around it in the horizontal plane, and it can see between 0 and 45 degrees up in the vertical plane. Okay, so it's seeing all around the room. And this next slide shows how it works in the robot. At the bottom here, you've got the scene from a colleague's house, and then this is the equivalent of the map that's been generated and the location within the robot's location within the room. So you can now see that as we kick off here, we're picking out a number of features from the room, and we're building a map of those features. You can see them represented here with their uncertainty. And then the robot is locating itself within the room, and you can see it doing this oil drop pattern while it does its clean. Okay, so the navigation system coming from the images allowing us to build a map which allows us to locate ourselves within that room. So that's the SLAM working on the robot. Okay, so we've discovered parts of the robot. Now, once we've assembled the robot, we have to do lots of testing on it, and many of these tests are to do with performance criteria. You know, how well we're doing cleaning. It's also got, you know, we need to consider, because we are using motors, you know, we have to consider how noisy the robot is. So we have, so we measure the noise of the robot. We also consider some robotic features, such as how often do we need to attempt to dock before we actually dock. So we need to take that. And actually, there is an IEC standard room for robotic vacuum cleaners, which is highly defined, with an area for which is a tiled area down here. There's also a table in the room. It even defines the lighting system and also posters or pictures on the wall. And then what we do is we start the robot off in 4 locations within this room. And then we can then determine things like what the coverage rate is, how much of the room has the robot actually covered. Is it a really low score? If it was 80%, then that would be not a very good coverage score. If you get into the 90s, that's a good score. And also the coverage rate. So how long does it take you to do a meter square within the room? So these are values that Dyson can use to compare with other robots, to see how well we're doing against our competitors. So that's just a little bit about measuring the overall performance of the robot. I've got this slide here, which is slightly a marketing slide, but it hopefully pulls some of the technologies together, and you can see this working. Let me just start this. So it's a little bit of a marketing slide, but hopefully just gives you a feel of what the robot's, how it's being used by the user. So somebody started it, they've gone off for a run, and then the robot comes off and it starts its clean. You can see the Dyson motor pulling the air through the system. You can see that it's picking up the dirt with the brush bar, which is the full width of the product. You can see the illumination coming on as it goes under a table. You can see it doing its square wave. And you can see the camera system there. And then eventually it comes back to its to the dock, and then it sends a map to the user to tell it how well it's done on that clean. So that's just a quick overview of the. It's a marketing video that hopefully pulls some of those components I've mentioned together. Just to end the kind of formal presentation, I'd like to show you some of the technologies that we're using now for the future in our simulation work, and also in some of our algorithmic work. So I'll start off by this shows one of the simulators that we used to develop. We used to develop our SLAM algorithm. I think there's somebody. That's right. So this was the algorithm for SLAM has to invert a large matrix, which can be a little bit sparse. So we have some optimization routines for these for this inverse of a large covariance matrix. So we have a simulator that performs that activity. So this is what we were using a while ago. We still use this in our current product. And this is another simulator that we use for developing our oil drop algorithm, and see how the oil drop algorithm works in the home. Okay. So using simulators is really useful, because what you don't want to do as a roboticist is to compile your code, take it onto the robot, take the robot into the lab, and then find that you've got a minus in front of a cosine where you should have had a plus, and then the robot will rotate the wrong direction. So we use simulators to get rid of those small bugs. But these are the simulators that we were using in the last generation of robots. For the next generation, we're going to be moving towards using not just corner features in the images, but we'll be using every pixel, okay, in the image, and using that as a feature. And then what we end up having is almost like a 3D reconstruction of the room. Okay, so this is now having each pixel as a feature, but it also gives us this kind of 3D image. And then there's a lot we can do with this, and I'll describe a little bit more of that later. But you can see that as well as the 3D reconstruction, we get the position of the camera. Again, we get an estimate of that. So this is some of our, some of the direction we're moving forward to in our algorithms. This is one of our advanced simulators. So we spend a lot of time giving users and trialist robots in order to test our robotic system. But now we're moving towards using more simulation. So this first part, it looks a bit like one of our old simulators that I showed you earlier. So this is just a plan view of the room. But that's actually based on a 3D simulation. So this is this is a simulated room. So we can move the chairs around, we can move the furniture around, we can change the types of carpets, we can change where the sun is shining, so we have different shadows within the room, and then we can test the algorithms, just by throwing compute resource at it, as opposed to taking it, getting lots of people to take it home on trials and doing stuff in the evening. So this is a fantastic technology which will speed up our development. And again, I could have this running continuously, so we could be testing rooms 24 hours a day and finding bugs or undesirable effects in the behavior of the robot, and then we can then fix those. So this is going to be really good technology for the future that will speed up our development and improve the quality of our product. Again, this is some of the work that we're carrying out at the Dyson Robotics Lab at Imperial College in London. I'll just show you this. There's a little video with this. I'll just show that. So what we're showing here is, again, using some of the advanced technologies where we're using every pixel. So we're not using corners of in images now. We're using all the pixels, and you can see this. We end up with this kind of 3D image, and then we run this through a neural network which does segmentation on the image. So now we can detect, for example, there's something in that corner. So we can do the segmentation, but we can also do the labeling. So then it's labeled as a bin. And then using that information, we can get the position of the robot within the room. And this is really useful for our navigation, because if I can pick out features like doorways or windows, then they're really good navigation features. Or if I can say there's a toilet, then I can say immediately, well, I'm in the bathroom and not in the living room generally. So this is, again, fantastic technology that we will endeavor to have in our future products. Okay, so that's just a quick overview of the Dyson, the 360 Heurist. Hopefully the students can relate to some of the work they're doing on their courses to and see how they could apply that to a mass market robot such as the 360 Heurist. And we've also had a look at some of the future technologies that will be in these types of robots, from using advanced simulation techniques to also using AI to improve our navigation. So if anybody's got any questions, I'd be happy to answer them. Tuan, are you still there?
I'm here. Any question?
Yes. If you field the questions, maybe Tuan, then that would be great.
Yeah. Các anh chị xem có câu hỏi nào thì đặt với Dr. Job. Any question, please?
Yes. Hi, Dr. Rob.
Hi.
Yes. Thank you very much for the presentation. Okay, just a brief introduction. My name is Lam. Currently, I'm working as the automation engineer in the manufacturing plant. So
fantastic.
Mostly I deal. Yes. So mostly I deal with AMRs as well, but more on the implementation side, not the the design process. Yeah.
Yeah.
So previously I was very fascinated by your team's choice for the so-called train track for the driving wheel.
Yes, yeah,
So,
yeah, yeah.
so, so based on my experience, normally the choice for the driving wheel is just a single wheel because when the robot need to rotate about its own vertical axis, it
Yes,
will
yeah,
minimize the friction against the floor. So,
yes, yeah, yeah.
could you enlighten me about this the judgment to use the train track?
Yes, yeah, yeah. So one of the things with using the tank track is that you can use two small wheels and the belt to represent a much larger wheel. So it can give you more mobility than just because I'd have to have quite a large wheel to get the same mobility as I can achieve with the two small wheels. So that's one of the reasons we went for the tank track arrangements, because we tried it in our development. We did in early developments we tried it, but we had to have quite large wheels in order to give us the same performance as the two smaller wheels with the belt. So that it was basically driven by mobility. If that
I
makes
see.
sense.
I see. So out of these wheels, so out of these two wheels, only one is the driving wheel. The other
Oh
one
no,
is the support wheel.
Oh no,
Oh,
they're both the traction wheels are driven. So we have, I think, 15-watt motors on each one, and they can be controlled independently. And then
I see.
there's a small jockey wheel at the back just to give it balance. So we can move forward, and then we can move backwards by driving them in the same direction, and then if we drive them in different directions, then we can get the robot to turn on the spot, basically. And for a round robot, that's really useful because we haven't got any sensors at the back, so we can drive forward and we can see where we're going effectively, and then when we want to reverse, we can actually rotate and then come back, and then the sensors then again allow us to see where we're going.
I see. Yes. Thank you very much. Yeah, that was very fascinating. Thank you.
Okay, no, thank you for the question. Nice to meet you. Yeah.
Next question, please. Dr. Rob, how your robots prevent your moving obstacle? For example, we have a child are playing on your floor, the moving obstacle. How to
Okay, right. Yeah. So there's two answers to that. I think is that it can affect if you have moving articles or humans in the room, then it can affect our navigation, because we're just taking features and those features are moving. But because we have this kind of 360-degree camera, and we're seeing all the way around us, then actually we have enough features for navigation. So if there's some are moving, it doesn't really affect our navigation capability too much. Okay, so that's one answer, that actually because we see all the way around the robot, having one or two humans in the room doesn't affect the navigation too much. And then the second part is with our sensors, when we build with our time of flight sensors, when we build an occupancy grid of obstacles in the room, if we then go back to that part of the room and the obstacle has been removed, then we it's like a counting system. So if we don't observe it for say 4 counts, then we'll remove it from the obstacle map. And then if we detect something else, then we'll add it to the obstacle map. So that's the second part, is for the time of flight sensors. We have an obstacle map which has got a counting system, so we need to see it a few times before we add it to the map, and if we don't see it for a number of times, we'll take it out of the map.
Okay, I see. Next question, please. Có ai hỏi câu hỏi gì tiếp nữa không ạ?
Hi, Dr. Rob. I want to ask you one question.
Yes, please. Yeah. Nice to meet you. Yeah.
I see that the job presentation is very good and fasting. So
Yeah.
I want to ask you one question.
Yeah. Please do. Yeah.
I do you do I can replace chips? Uh, I want to ask that I if I can replace Raspberry 4 and Arduino to control robots. And what difference? What are difference when I use Raspberry and Arduino to replace
Right. Yeah.
to replace chip the chip?
Okay, right. So you're saying if we use if you were to be able to replace the processors by a Raspberry Pi, is that the?
And Arduino.
Yeah. Yes. Yeah. I think you could replace the processing architecture with a different architecture. But it would take you a long time to develop the code to control all the motors and the cameras and things. We have quite a large team on this robot. The software team would have been about 40 people. For the next generation of robot that we're working on today, the team is much larger. So trying to change the processes. For an individual would be quite difficult because of all the software that would be required to run the robot.
Thank you very much.
Okay, thanks. Yeah.
Any question? Any question, please?
Can I? Hello.
Hello. Yeah. Hi, pleased to meet you.
In your research, you use SLAM and also camera to create a map. So, did you have a mathematics model to create the map?
Yes. So I think your question is, do we have a mathematical model for the unraveling? Is that where we take the polar?
Two sensors create a map. So how you combine the two camera?
Yes. So
how you combine two sensors?
Yes. Well, in fact, we don't. The camera system just tells the robot where it is. So it just provides the navigation capability. We don't use the camera for feature detection on the current for obstacle detection. So we don't use the camera to detect walls or anything like that. It's just purely for navigation. And the algorithm in it is it basically the first thing we do is unravel the algorithm. So the image is in a polar coordinate frame, and then we take it into a rectilinear. And then the second part is that we pick out the features, which are corner features effectively from the image, and use those for our features, which are in 3D. But when we take it into the SLAM, we flatten the 3D into a 2D arrangement, and then that's how we run the algorithm. But the camera isn't used to detect obstacles. It's only used for detecting image features, which are squares, which allow us to do the navigation, and it also picks out the fiducials, those black and white parts of the dock, in order to get fine alignment when it's docking as well. So hopefully that answers your question.
Way.
Dyson camera give you
Rectangle
2D
way.
X-lamp give you 3D.
Sorry,
I mean, how
could you repeat the
you
question,
use
please?
camera. So in your F-film, the camera will give you 2D, and the X-lamp you can create 3D.
Yes. So we get the 3D. We go from the 2D using because the camera is calibrated. We can then get to a after grabbing a few frames, we can get to 3D, and then we flatten that down into a 2D X and Y because the robot is basically moving in a plane. So yes, so that's how the algorithms work. Yeah.
What about the coordination? How you can detect the coordination?
So
You have a lot of fun.
sorry, can you repeat the question, please?
About the coordination. So you need to have a reference coordination.
So yes, to give us scale, what we use is that we've got wheel encoders on the robot, so that as we move from one position to the next and then get the next image, then that gives us the kind of scaling factor that we need to give for the SLAM.
So the final question: have you use any the filter in the sensor, like Kalman or some of filter you use in the device?
For future SLAM technologies. So again, we're looking at different techniques. I can't tell you what, because Dyson's quite a secretive company, so I can't tell you what we're working on now. But in the Dyson Robotics Laboratory, we are moving towards using what we call dense SLAM, where we're using all the pixels in the image. And I think there's value also in when you have these dense reconstructions, then by using neural networks to segment and label the images, it's a very powerful navigation tool, because if I can determine doorways and windows, then my navigation becomes really good. If I'm detecting things like children's toys or chairs, because chairs tend to move, then my navigation isn't so good as if I've got extremely fixed features that I can use for navigation.
Okay, so thank you so much.
No, nice to meet you. Thank you for the questions.
Mr. Robert,
Yeah.
I have one more question for.
Yes, no, please, yeah, carry on. Yeah.
Can you explain more clearly about how the robot can recognize where it can charge when power is limit?
Right. Yeah. Yes. So with the right. Yes. So when the battery is low on charge, is that? Yes. So what happens is that on this robot, the robot monitors the voltage of the battery, and as the battery moves to being depleted, the voltage will drop on the cells. So what we do is the robot will go out and clean, and when the voltage drops to a certain level, we then know that we've got 15 minutes of time to get back to the dock to recharge. Okay, so then we will then move back to the dock, recharge, and when we've recharged to about 80%, we will go back out to where we were just before, and then carry on the clean from that point.
I mean that how the robot can find the way to return where to return where the robot can charge more.
Yes. So to get back to the dock, because it's from the minute it comes off the dock initially, it starts building up a map, using these features, and then it'll move around the house. It might go into a different room, but it still knows where the dock was, because that's its starting point. So because it's got this SLAM map, it can then maneuver itself back in front of the dock, and then it just uses the fiducials for fine alignment. So it's basically, because we have this SLAM map, we can always make our way back to the start position where the dock is.
Okay, thank you very much.
It can't cope with what we call dock kidnapping. So if you take the dock and then put it somewhere else, while the robot is still cleaning, it'll go back to the initial position and then won't find the dock. So we have to leave the dock where it is once the clean is started. Otherwise, it confuses the robot.
Thank you very much.
Okay, thanks.
Okay, without any question, thank Dr. Rob so much. Thanks speaking again so much for your exciting and wonderful and very informative talk. So, hope to see you all in the next if we have a chance.
Okay, great. Okay, well, thank you much for hosting me. It's been a pleasure to talk to the students and to the academics, and thank you very much for all your thought-provoking questions. Thanks now. Bye.